Okay, so today we're going to be talking about Smart HRG versus the standard HRG. HRG stands for high resistance grounding, and that will be the focus of our discussion today. So we're going to be briefly talking about iGard as a company, and then we're going to go into what constitutes a ground fault in a system. We'll also be discussing types of grounding systems, including a more in-depth focus on resistively grounded systems and how we can transition to a resistance grounded system, depending on if we're solidly grounded or ungrounded. In addition to that, I'll go over the sizing of the NGR, what factors are important that we need to consider, and I'll also be discussing our standard HRG offering as well as our smart HRG offering, as well as what code and standards requirements are indicating for high resistance grounding. So this is our facility in Mississauga. We've been manufacturing resistors for 40 plus years since 1982. And we also purchased the Federal Pioneering Division, a relaying division from Schneider Electric in 2003. So we have 20 years of experience in manufacturing relays as well. On the left-hand side here is our resistor manufacturing section, and on the right-hand side is our relaying manufacturing area as well. Now, when it comes to ground faults, a ground fault is an unintentional path between conductors and ground that we want to avoid because it may cause damage to equipment and personnel. This is usually caused by loose connections, worn wire insulation, exposure to moisture, or even external natural conditions. Now, in the North American market, we typically see three different types of system grounding arrangements often utilized. Ungrounded systems are utilized about maybe 12 to 14% of the time. It allows for continuous operation in the event of the first fault condition. The only issue is that when a first fault occurs, there may be transient overvoltage conditions which could arise from the unfaulted phases, which could exceed up to 6 to 8 times the line to neutral voltage of the system. This could cause further degradation in the cable insulation and eventually lead to a phase-to-phase failure if it's left in the system for too long. In addition to that, it's very difficult to locate faults in this type of system since there's no ground return path for the fault to circulate through. So what the North American market did was they addressed this with the solidly grounded system, where you have a delta to Y configured transformer, and typically the exo point of that transformer is solidly grounded to ground. That allows them to eliminate transient overvoltage conditions by shorting out the capacitance that exists between conductors and ground. The only issue is that when we detect a fault, although we can locate very easily, we have to trip the fault right away because otherwise there would be circulating fault currents going back to the source in the magnitude of thousands of amps or more. And that could cause an arcing condition, which is problematic. So in the case of a solidly grounded system, you're reducing the transient overvoltages, yes, but you're compromising process continuity as a result. The in-between ground between ungrounded and solidly grounded systems is a resistance grounded system. In a resistance grounded system, we're essentially limiting the fault current to a specific value in an effort to not allow the arc enough energy for it to build up to a higher level of power. In addition to that, we size the resistor in accordance with the charging current coming from the capacitance in the system such that we can control the transient overvoltage condition. And we can also easily locate faults in this system since the technology is very similar as with the solidly grounded system. And also we have pulsing feature on our resistors, which can help in locating faults. So it's now practically used everywhere where data centers, hospitals, and other process industries which can't tolerate a fault are utilizing this type of technology. In this particular schematic, we have a 480 volt line-to-line voltage system. And as you can see, we've placed a resistor from the neutral point to ground with a resistance of 55.4 ohms. Effectively, this resistor will limit any future fault occurring in the system from phase to ground to 5 amps. Our line to line and line to neutral voltages are still intact at the moment because there's no fault in the system at 480 volts and 277 volts respectively. Now let's see what happens when a fault occurs in the system. So the fault occurs on phase C. So phase C ends up getting faulted, and the fault current will take the path through the resistance up to the neutral point and down through the C winding back to the point of fault, because current likes to close its loop. So now we have this circulating 5 amps of fault current. Our neutral gets elevated to the line to neutral voltage of the system at 277 volts, line to neutral. And our unfaulted phases will get elevated to 480 volts, line to ground. This will effectively give us 480 volts line to line to continue our process, even with respect to the faulted phase and the unfaulted phases. So at this point, we haven't really tripped anything. We've experienced our first phase to ground fault, and we're limiting that fault current to a specific value. Now, when we're considering a resistance grounded system, we have to ensure that the cabling is rated for the line-to-line voltage of the system. As seen in the previous slide, we had a phase to ground fault that caused elevation on the unfaulted phases. So we need to make sure that our cabling, our lighting, and our surge arresters are also rated for the line-to-line voltage, such that it can handle that voltage stress during the first phase to ground fault. When it comes to VFDs, surge protection devices, and UPSs, we have to ensure that they're compatible with the HRG system. Sometimes VFDs may have a direct connection between their conductors and ground, either before the rectifier circuit or after the rectifier circuit on the DC link. And as a result, that may bypass our resistor and no longer allow us to limit fault current to a specific value, since the ground fault will take that path through the VFD back to the ground fault point. In addition to that, it is highly recommended that you do not utilize single phase loads with a resistance grounded system, simply because the neutral gets elevated to the line to neutral voltage of the system. So that poses a problematic scenario for single phase loads that are relying on one of the phases as well as the neutral. When it comes to insulation levels for cabling in high resistance grounded systems, for systems up to 5 kV, you don't need to worry about what IEEE 242 says, because most cabling is already taking into account 173% insulation level rating, where you can hold the fault for longer than 1 hour continuously. In the case of low resistance grounding, where it's utilized on higher kV values, let's say 15 kV or 13.8, let's say, consultants can use either 100% or 133%, depending on how long they're leaving the fault in the system. But usually for these higher voltage systems, they're typically tripping on first fault and coordinating accordingly with their feeder circuits downstream to isolate the point of fault before the main circuit breaker upstream trips. Now, here's an example of how we utilize single phase loads on a resistance grounded system. At the top section, we have a high resistance grounded 480 volt system, which is 3-phase 3-wire, handling 3-phase loads such as motors. And then we've placed these 2 isolation transformers here to convert the system from high resistance grounding back to solidly grounded, where we can now have that distributed neutral to satisfy single phase loads such as lighting. In addition to that, for the loads at 208, 120, we can satisfy that by also going to solidly grounded and satisfy computers and outlets that are most commonly utilized. Now, if your customer has an ungrounded system and they're complaining about transient overvoltages and difficulty in locating faults that are existing in their system, one way that we help our customers is we implement a zigzag transformer connected to the 3 phases. And this zigzag transformer establishes an artificial neutral, in which case we can connect a resistor from the artificial neutral to ground. This resistor does quite a few things for the system. One, it controls the transient overvoltage scenario that would otherwise occur in an ungrounded system. 2, it provides a ground return path for the ground fault that is occurring in the system so that we can actually quantify how much magnitude that ground fault has. And in addition to that, we're able to locate the position of the fault provided that this resistor has a pulsing feature, which we will get into shortly. For sizing of the NGR, there are 5 concepts to consider. That is rated voltage, rated current, rated time, the maximum temperature based on the time rating of the resistor, as well as the temperature coefficient of resistance for the particular alloy that is utilized in the construction of the resistor itself. With respect to rated voltage, it really depends on the type of system that you're specifying. For 13.8 kV generator, for example, we're insulating to the line to neutral voltage of the system. So in this case, we would be insulating the neutral grounding resistor to 8,000 volts line to neutral. When it comes to rated current, usually for low voltage systems, 5 amps or 10 amps is selected for 480 volt and 600 volt systems. And for systems that are approaching 4160, 13.8 kV, and 25 kV, we need to entertain a concept called charging current, and we need to calculate how much charging current is to be expected from the system in the pre-design stage. Now, charging current is based on the idea that there is a capacitance that exists between conductors and ground. This capacitance basically is dictated by the amount of cabling that you have leading out to the loads, as well as the loads themselves and the source itself. The loads and the source do not contribute as much. It's more so the cabling. So if you look at your cabling data sheets, there will be a value for how much capacitance that you have per 1,000 feet. In this case, you can use that to calculate your capacitance. And then once you have your capacitance, you can calculate your reactance by doing 1 over 2 pi FC, and then divide that reactance by your line to neutral voltage of your system to get the charging current per phase coming from that capacitance. Once we multiply that charging current per phase by 3, we have our total system charging current capacitance from the 3 phases themselves. As a result, now we can determine how we're going to size our resistor. The idea is to size the resistor equal to or greater than this system charging current, such that we can control the transient overvoltage condition. If we don't size higher than the charging current, then the transient overvoltage condition on the unfaulted phases may exceed that line-to-line voltage rating. For the duty cycle of the resistor, it really depends on whether you have process continuity or not. Usually for 480 volt and 600 volt systems, we specify a continuous rated resistor. As we get to systems that are tripping on first fault, usually we spec out 10-second or 60-second rated resistors. Now in Table 9 of the 295 standard, which governs for neutral grounding devices and the construction of them, we have to follow Table 9's temperature rises for depending on whether we're specifying out a continuous rated resistor or a 10-second or 60-second rated resistor. For continuous rated resistors, our requirement from ambient is very stringent in being within 375 Kelvin. When we have a 10-second or 60-second rated resistor, we have much more room at 765 kelvins, and as a result, that gives us more capability in providing a more economical solution and a smaller footprint for this neutral grounding resistor. So a 13.8 kV 10 amp 10-second rated resistor versus a 13.8 kV 10 amp continuous rated resistor, the size will be very drastically different, and the cost will also be drastically different as well, with the 10-second rated resistor being more economical and lower footprint. Now, for the sizing of the NGR, let's look at this example where a consultant has specified a 4160 volt line-to-line 400 amp 10-second rated resistor. In this case, the maximum temperature rise based on the table in the previous slide is 760 degrees Celsius. Based on the 295 standard in 6.2.1, it says that the current shall not vary from the rated current by more than 20%. Below, we are looking at 4 different alloys, each with a different temperature coefficient of resistance. The way that this coefficient of resistance work is that the lower the number, the lower the resistance will change as the temperatures increase. As you can see in this table below, these 3 alloys here are not able to meet the requirement of being within 20% of its rated current, simply because as the temperature rises, the resistance changes so drastically that the current ends up decreasing beyond 20%. Whereas the 1JR alloy, which is used on many of our resistors that we manufacture, is staying within those boundaries of being within 20%. Now, in the Canadian Electrical Code back in 2015, we really didn't have a reference for impedance grounded systems, but due to a lot of requests from consultants that are speccing out impedance grounded systems, they decided to implement some clauses in Section 10 of grounding and bonding. Further to this, in 2021, they gave us a really nice table called Table 17. Table 17 gives you the instances of when we have to initiate alarm or de-energize the system based on the condition that we're facing. As manufacturers of resistors and the relays, we have to also monitor for ground faults in the system, which is denoted by this column here. We have to look for short circuit condition on the NGR, which is denoted by this column in the middle. And also we have to also monitor for the open circuit scenario on the NGR, which is a loss of continuity from the XO point to ground. A lot of consultants are taking advantage of the fact that in a 3-phase 3-wire system where we're 5 kV or less, or if ground fault current is limited to 10 amps or less, we have the ability to alarm the ground fault without tripping, provided that we're using a continuous rated resistor. Because here it stipulates you alarm and de-energize the system within the time rating of the impedance grounding device. But if the time rating of the impedance grounding device is continuous, then we only have to alarm the condition of fault and continue with the process without tripping anything. For the short circuit scenario, we have to alarm and de-energize the system within 48 hours. And with the open circuit scenario, we either alarm if we can still detect a ground fault in an ungrounded system, or we have to alarm and de-energize the system within 48 hours. Now, on this portion below, on the 3rd row here, it says that if you have a system that's greater than 5 kV, or if ground fault current is being limited to a value greater than 10 amps, then we have to alarm and de-energize the system within the lesser of 48 hours or the time rating of the impedance grounding device. But typically, consultants don't want that much wattage flowing back to their source. So to put into perspective, if we have a 600-volt system that has a 10 amp NGR, we're going to expect to see 3,470 watts flowing back through the neutral point up the resistor. In contrast, if we have a 13.8 kV system that also has a 10 amp NGR, that would be 80 kilowatts circulating. So typically for this section, consultants that I've been working with have been speccing out either a 10-second or 60-second rated resistor, and then tripping on first fault with coordination with their downstream feeder protection. The short circuit and open circuit scenarios for this particular row remain the same as the previous row. And in addition to that, I did skip over this first row. It's because I mentioned to you at the beginning that we should not be distributing the neutral in a resistance grounded system, simply because on each of these conditions, we have to alarm and de-energize the system immediately. So really, resistance grounding doesn't provide a benefit when you have a 3-phase 4-wire system. So to summarize for you guys, let's say you've done a charging current calculation on your system and your system is below 5 kV. You realize that that charging current is below 10 amps. You size your let-through current of your resistor greater than the charging current, but less than or equal to 10 amps. That gives you the ability to alarm on ground fault while maintaining operation, assuming that you're using a continuous rated resistor. You're also satisfying arc flash mitigation as per NFPA 70E and CSA Z462. When it comes to low resistance grounding, we're focused more on seeing how that charging current is going to be greater than 10 amps or not, and if your system is greater than 5 kV. In that case, we size our let through current greater than our protection pickup at our feeder level, and then we have it as time rated and tripping on first fault. This is our Sigma 3-C. It's an NGR monitoring relay and ground fault relay. It's able to detect abnormalities on the neutral grounding resistor, as well as monitor for ground faults flowing through the neutral. It has an operating range between 480 volts to 69 kV. The way that we do the resistor monitoring is a bit different in comparison to the competitors in the market. The way that we do this is that we're applying a sensing resistor between the XO point and ground, as well as a CT that's located to detect how much current's flowing through the neutral. Our sensing resistor also gives us a reference voltage for what's happening at the XO point. Now, if there's 0 volts and 0 current, we still have to monitor this neutral grounding resistor for open and short circuit scenario. So the way that we do that is we use a high frequency AC injection method that takes the path up through to the sensing resistor up to the XO point. And because the high frequency AC injection sees this inductance on these 3 phases as a higher impedance than the NGR itself, majority of our signal takes the path down the NGR and gets confirmed at the relay. Many of what's out in the market right now is using a DC-based injection method, and that DC-based injection method, when it reaches this XO point, it sees these inductances as short circuits. So if you have YY connected PTs in your setup, the DC-based injection that the competitor is using may find an alternative path, and in which case it may falsely presume that the NGR is still in the system. So that's the way that we've mitigated that with our high frequency AC injection. And we have 2 different modes of operation. We have a continuity mode and a measurement mode. In continuity mode, we're constantly injecting that high frequency AC injection to confirm that the NGR is still able and still within the system. When we get into a measurement mode, that's when we're detecting some voltage and some current on the neutral. That allows us to back calculate what the resistance is at the neutral by dividing voltage over current. As a result, we can compare that measured resistance value with the actual value of resistance that was set during the time of commissioning. And if it's beyond 150% of that value or below 66% of the value, then we're indicating an NGR fault scenario. With respect to pulsing, this is a method in terms of locating faults in a resistance grounded system, provided that you have process continuity. Let's say, for example, that motor 3 experiences a fault on phase B. Now we've detected that fault at our CT neutral, and we've now alerted the maintenance that there's a fault in the system. Maintenance now knows that there's a fault in the system, but he doesn't know where the fault's coming from. So what he can do is he can implement the pulsing feature off of our touchscreen display. The pulsing feature basically opens and closes this contactor that is shorting out half the resistance. As a result of shorting and opening this contactor, we're adjusting how the current signature is flowing back to the point of fault. So it's flowing between 5 amps and 10 amps, or 2.5 and 5 amps. And it's going to take the path of fault, and you may use a Rogowski coil hooked up to your Fluke multimeter in terms of locating the position of this fault and tracking and providing corrective action. So far, our standard HRG offering is taking majority of the advantages of ungrounded and solidly grounded systems while eliminating majority of the disadvantages. The only thing that we're missing is process continuity in the event of a second ground fault condition, as well as arc flash mitigation for safety. So Smart HRG is where we can make this stance. Smart HRG is an acronym for Selective Instantaneous Feeder Tripping, Main Time Main Coordination, Assisted Fault Location through Feeder Identification, reducing both the likelihood and magnitude of exposure for arc flash mitigation, as well as time-selective feeder isolation. So for selective instantaneous feeder tripping, let's say, for example, we're experiencing a fault on feeder 1, phase A. That fault is now being limited by this NGR, and we haven't tripped this fault open. Our DSP system is monitoring the resistor as well as all these 3 feeders. When another fault occurs on another feeder on another phase, what happens is these faults are now going to be circulating between each other, and the neutral grounding resistor is out of the game. It cannot limit the fault current to a specific value because now we're experiencing a phase-to-phase failure, and the current between these 2 points is building up. As a result, if we didn't have our DSP system here, the instantaneous function of these 2 breakers will effectively trip out, and we'd lose power to both of these feeds. But with our DSP system, we can assign priorities to each of the feeders based on the criticality of those feeds and trip the lower priority feeder in favor of keeping the higher priority feeder still in play. So only tripping one out of the 2 and reverting us back to the first fault condition, where the remaining fault will now circulate back through to the NGR to be limited. In addition to that, we also get involved in quite a bit of main-time-main applications, such as for hospitals and data centers. And as a result, we have a system that is compatible with such a configuration. We place our DSP system on the left-hand side, monitoring the resistor on this transformer, and we have another DSP system on the right-hand side, monitoring the second resistor's transformer and its associated loads. When the tiebreaker closes here, we get a signal that the tiebreaker is closing, and the DSP system on this side will transfer over all of its readings to the DSP system on the other side to unify the priorities along the entire bus and continue monitoring these 3 feeders that are kicked out because this transformer was taken out for maintenance. Now, heading into NFPA 70E, NFPA 70E is a standard for electrical safety in the workplace and is based off the US standard. This also is mirrored for the Canadian market in CSA Z462-21. In Annex O.2.2, it says that design option decisions should facilitate the ability to eliminate hazards and reduce risk by doing the following: reducing the likelihood of exposure, reducing the magnitude or severity of exposure, and enabling achievement of an electrically safe work condition. Further to this, in Annex O.2.3, they list out 9 different incident energy reduction methods. Of the 9 that are listed, high resistance grounding is the only one that's reducing the likelihood. All of the other incident energy reduction methods are acting after the fact that the arc is already in the system. So for high resistance grounding, we know that if it's a phase to ground fault, we're limiting that fault current's magnitude to a specific value. And we know that 95% of electrical faults begin as single phase to ground faults. So when we select a low enough let through current, there's insufficient energy for the arc to restrike, and as a result, it self-extinguishes. The only issue with resistance grounding is the phase-to-phase and phase-to-phase-to-phase failures where our neutral grounding resistor is no longer able to limit the fault current. So although HRG is able to reduce the likelihood, it can't reduce the magnitude because the magnitude is also taking into consideration phase-to-phase and phase-to-phase-to-phase failures that are occurring in the system. So what we did at iGard is we implemented an arc flash detection relay alongside our resistance grounding solution so that we can handle the magnitude approach by capturing the particular spectrum of light emitted by an arc flash incident and tripping the upstream breaker within 1 millisecond is when we're sending the signal out. Now, with the combination of this arc flash relay and the high resistance grounding system, we're essentially meeting Annex O.2.2 and reducing the likelihood of exposure, reducing the magnitude of exposure, and enabling achievement of an electrically safe work condition. So now you can see that Smart HRG is advancing on just the standard HRG offering and providing these additional benefits of second ground fault protection, as well as arc flash mitigation for safety. And here is the modular solution that we've provided to our customers for many years. We have our arc flash detection module on the right, our main time main module. We have feeder modules, resistor monitoring relay, our DSM, which monitors the voltages between the phases as well as to ground, as well as the neutral voltage. We have our power supply here, which controls the pulsing signal for the resistor for fault location, as well as powering all of these modules that are hooked up by ribbon cables between each other. All of this information is connected to our communication module, which sets up to this nice touchscreen display. This touchscreen display is very intuitive and useful to use in providing information to maintenance and end users on how much magnitude of ground fault there is in their overall system, how much ground fault there is at each individual feeder. We can indicate what phase is faulted. We can trip on first fault or second ground fault, depending on your preference. We can indicate phase loss. We can indicate a bus fault. We can provide the data and event logging on all of the incidents that are occurring in the system, and we can provide that information via Modbus TCP IP as well. We also provide trending analysis to see how the ground fault is developing. Usually for ground faults, they don't appear as bolted faults right away. Sometimes they appear as resistive faults, and they slowly begin to gain more and more fault current as time progresses on. So maybe in January, when you're doing, an inspection of a chiller or a blower, you can see that the prospective fault current is at roughly 12 milliamps right now. But then you check again in March or April, and then that could be jumping up to 32 or 35 milliamps. We want to be able to provide predictive maintenance so that we can schedule our shutdown and look for the issue that is causing that feeder to experience these fault currents that are being read by our relay. So that's basically the presentation. Let me know if you have any questions. I think I can open up the chat now to see.
Okay, Sonny, thanks very much. Good presentation. Yeah, we have a few questions here. Which one is the best to be used in relation to low and high resistance grounding?
So for what I mentioned before with respect to low resistance grounding, typically we utilize that on 4160 volt systems and higher. 4160 is the range where there's the discrepancy between high resistance grounding and low resistance grounding. It mostly comes down to the charging current calculation, which you will do on your system. The charging current is dependent on how much cabling you have leading out to loads. If that charging current of your system is within 10 amps, then you can still satisfy process continuity and go ahead with high resistance grounding for that 4160 volt system. If the charging current is greater than 10 amps, then you need to rule out HRG and use low resistance grounding and coordinate with your feeder protection, whether that's LSIG breakers or an SCL relay or a GE multi-lane relay, whichever one you're utilizing. Usually for higher kV systems, when we get past 5 kV, it's almost all exclusively LRG. And in that case, LRG means that you're tripping on first fault and you're just coordinating with your feeder breakers downstream.
Okay. What is the best tool to size NRG or HRG?
The best tool would be to do that charging current calculation, to look at your cabling data sheet, understand how much capacitance that you have per 1,000 feet of cable, as well as determine what size of cabling you would be utilizing. There's some good white papers out there. One was by D. Baker. It's a very old white paper in which he takes you through the process of doing the charging current calculation. The only right way to size the NGR is to understand how much charging current there is in your system first, and then size in accordance to that. After that, the rated voltage and the duty cycle is going to be dependent on that charging current that you specify.
Okay, great. Who will decide lower priority and higher priority circuit breaker loads?
So with respect to that, I usually talk to consultants about which feeders are more critical and which feeders are less critical. So in some cases, like for a hospital, for example, you have a feeder that's feeding an operating room, and then you probably have another feeder that's feeding a blower or a chiller for HVAC. In this case, the higher priority will go towards the operating room, and the HVAC may be at a lower priority, in which case we would want to trip out the HVAC first in the event of a second ground fault scenario over trying to trip the operating room that needs that power to continue it having the doctors do the operation.
Yeah, you don't want to lose power when you're having brain surgery, right?
Yeah, absolutely not. No.
Yeah. Okay. Can resistance grounded systems be modeled in software like PTW32 and Easy Power? And will it reflect in the calculations to reduce incident energy levels?
So for the calculations to reduce incident energy levels, I mentioned to you that resistance grounding is only reducing the likelihood and not the magnitude. As a result, incident energy levels are taking into account face-to-face and face-to-face-to-face failures when they're doing those calculations. So it's not going to reflect in reducing those incident energy levels. What it can do though is for phase to ground failures, it can limit that magnitude. So that's what you can utilize for Easy Power and PTW32. I know that they have an option to place resistance grounding. I just don't know. I'm not. I haven't tinkered with those particular softwares. I've utilized ETAP, and I think ETAP does have it.
Okay. Does your grounding system effectively affect the parallel transformers?
So when it comes to the grounding configuration of other sources, let's say if we have 4 generators in parallel on a paralleling bus, those generators need to also match the resistance grounding system that we're specifying. So for each of those generators, it has to be resistance grounded. If you have transformers that are operating in parallel with the generator side that is resistance grounded, then the transformer should also be resistance grounded to match the offering if it's a peak shaving application where these generators are cogenning alongside the transformer to save the customer cost on energy, for example. In the case where a transformer is only supplying by itself, then you can use that resistance grounding. And if you have paralleling transformers, not there won't be 2 transformers operating within the same interconnected system, so they would typically be separated from each other.
Okay.
Uh,
Just hang on here. Let's see. Can you please repeat the last name of the author of the white paper you mentioned for calculating the charging current?
it's a Baker, Baker.
Okay,
Baker.
and Anna asked that question. Anna, if you write to Sonny, you've got his email address.
I
Perhaps
can send that to you.
he can send you the white paper. So that would be helpful. Great. Next one. Local utilities supplying 750 volts AC and less services do not allow resistance grounding of neutrals. Do you work with utilities to allow HRG?
So some utilities want to use solidly grounded or ungrounded when they're supplying to their customer. Uh, we we do not have any say in that approach, but we have worked with some utilities in BC and Alberta on that point. I know that other utilities are on a more stricter mandate to maintain solidly grounded or ungrounded depending on their type of configuration. So we don't really dictate that. It's more dictated based on the authority having jurisdiction and the hydro company having jurisdiction within that area. And we just comply with them. If the customer ends up having a customer transformer on their side that can bring in that utility power and then step down further or maintain the same voltage, then we can apply that resistor on the secondary side since that's customer owned. But if it's a utility owned transformer and they're specifying that they want it grounded a certain way, then we cannot interfere with that process, unfortunately.
Okay. Razvan has a question. How do we know when and where we can use one of these ground protection method models?
So if you have a system that doesn't have that many single phase loads or no single phase loads, then it's a candidate for resistance grounding. And depending on the voltage that you have, if you're at less than 5 kV and your fault current's less than 10 amps, then you can have the advantage of process continuity. So typically what consultants do is they give the option to the end user whether to go solidly grounded or resistance grounded, but then indicate that the resistance grounding has the benefit of process continuity, as well as controlling transient overvoltages such that they can have continuity of operation, right? So it really depends on the type of system that you're specifying. For systems that are greater than 5 kV, obviously majority of those are three-phase three-wire, in which case low resistance grounding has a benefit in limiting fault current to a specific value such that we're reducing that wattage flowing back to the source and allowing for reduced incident energy for phase to ground faults specifically.
Okay. Are you aware of protection issues with energy storage systems designed to reduce power demand?
I am not aware, to be honest, on that point.
Okay. All
For
right. Well,
energy source system.
no, that's fine. Thanks. Yes. Thanks very much for the presentation. Excellent presentation. Everybody's thanking you in the chat. We appreciate that. And thank you for asking those questions. This live online forum had a lot of questions, and that's good. There's no such thing as a stupid question. Let's see. Oh, one more just came in. Is there any coordination between busbar reactor and NGR?
I'm not, I haven't been involved in a busbar reactor application, but I have seen neutral grounding reactors, which are slightly different than neutral grounding resistors. That's the only reactor I've seen, but I can inquire about that and I can probably get back to you if you're able to send me an email. The
Yeah,
email
that's
I
from
can
Isaac
provide.
Paby. Yeah, Isaac, you can contact Sonny by email, and he can confer with you later about that. So
I
thank
put
you
my
very much.
email in the chat too, as
Yeah,
well.
there it is there. It's in the chat. Thank you very much, Sonny. That was a great presentation.
I
And
appreciate
thanks
it.
for everyone for the questions. Thank you to Justin Gall from CBS ArcSafe and Jim Chastain from Easy Power and Sonny from iGard. Thank you for the presentations.